Hello, today we'll take up the electrophilic substitution reactions. Okay, so an electrophilic substitution reactions may be represented by say R and L, say Levin group, where L is the Levin group, E is electrophile, so the product will be Re plus L positive charge. Okay, so an electrophilic reaction I write down here, and an electrophilic reaction, electrophilic substitution reaction may be represented as follows. So Rl is the organic substrate, E plus is the electrophile, so L is substituted by E, so we have the Levin groove. So here the Levin groove, L is displaced by an incoming electrophile E positive. So here the Levin groove L is displaced by an incoming electrophile E positive. Okay, so L is displaced is substituted by E represented by E positive. So an incoming E positive, the electrophile may be positively charged species like nitronium NO positive. So I can write down here. And incoming not Levin group, incoming electrophile E positive electrophile may be a positively charged species like NO2 positive charge, nitronium ion NO positive, and then Br Cl positive, I R positive, alkyl positive, RCO positive, etc. Okay, these things are the electrophilic incoming electrophiles. So maybe they are mostly on the positively charged species like this. So we will discuss one by one of these things. So here maybe the incoming electrophile may also be neutral compound, neutral species like Lewis acids. So I'll write down here the electrophile, the incoming electrophile may be an uncharged electron species, electron deficient species, so like Lewis acids, species like or an ion. Okay, so like for example BF3, etc. So they have the weakest Lewis acids are the best Levin groups. Okay, Levin electrophiles, or you can Levin groups or electrophiles. Okay, so these are, so we have discussed about electrophilic substitution reactions, where a Levin group is displaced by an incoming electrophile positive. Incoming electrophile may be positively charged species and may also be uncharged electron deficient species such as ion or BF3 like this. The weakest Lewis acids are the best Levin electrophiles. Aliphatic as well as aromatic compounds undergo electrophilic substitution reactions. However, these are characteristic reactions of aromatic compounds. So we can say electrophilic substitution reactions can undergo by aliphatic as well as aromatic compounds. So I write down here aliphatic as well as aromatic and compounds undergo electrophilic substitution reactions, but mostly found in the these aromatic systems. Okay, nevertheless, you can say nevertheless these are the characteristics of, then mostly found in aromatic system, characteristics of electrophilic reactions of, you can say reactions of aromatic compounds. So these are found mostly in the aromatic system as compared to aliphatic systems. However, the electrophilic substitution may be classified as, however, the aliphatic electrophilic substitution reactions may be broadly classified as like SN1, SN2, it also may SE1 and SE2. Then we can discuss SEI also. So may be classified as mostly aliphatic electrophilic substitution reactions may be probably classified as SE1 and SE2, just like necrophilic substitution reactions, like SN1, SN2. They are almost only the one is attacked by necrophile, another one attacked by electrophile. So let's see one by one the SC2 and SC1. Okay, so SC2 we can represent that, suppose this is a living group, the electrophile, then we have E positive, then we have the living group delta negative, okay, to negative, and this is a living group L positive charge. So these are intermediate, we can say. Then we can have this just like necrophilic substitution reactions. So this is the product, and this is where this is the for SC2, okay, bimolecular systems. Similarly, SC1 also can represent that. So this is the same living group, let's say, and then first step is formation of carbon ion, or a complex is from first intermediate, negative, positive, and then come to carbon ion, and then this second step is this carbon ion reacts with this electrophile, then we can have this E, okay, plus is a racemic mixture, so you can attack from this side, also there is inversion or tension or complication. So racemic mixture, okay, racemic mixture. So this is the first step for SC1 and second step for just like SN1, SN2. So I'm repeating again, the reaction in which the transition steps, the rate determining steps involve one species. You involve one species in the transition step, then the reaction involve only one species, then only one species here. And then we have this rate determining step is SC1 electrons. On the other hand, transition rate determining steps of SC1 reaction involves two species. If it involves two species, then we have the SC2. So when the transition state of I am repeating again, the reaction in which the transition state of the rate determining steps involve one species, then they are found in SC1. Okay. However, on the other hand, if the transition state of the rate determining rate limiting step of an AC reaction, electrophilic substitution reaction, involves two species. If the electrophilic substitution reactions involve two species, then the reaction is said to be SE2. So similar like earlier one cases in the electrophilic substitution reactions. So in an SE2 reaction, on an aliphatic carbon system, the bond formation and bond breaking occur simultaneously. That is concerted. While in an SE1 reaction, these are two separate steps. The reaction takes place through a carbon ion. So I'm repeating again that in the case of SE2, bond breaking and bond formation takes place simultaneously. That is a concerted mechanism. But in the case of SE1, it takes place in two steps. First is the formation of carbon ion, then carbon ion is attacked by the electrophile. Okay, so this is the carbon ion formation takes place. So this is quite difference in the case of SN1, carbocations form, but here SC1 we got a carbon ion. Okay, in SC2 reaction, inversion configuration takes place here. So another one is that the SC2 inversion configuration takes place. And here retention as well as the inversion takes place. So here retention, and there is an inversion. Okay, so retention product, inversion product. We got a racing mixture like earlier cases. So while racemization, so I'm repeating again, in SC2 reaction, inversion configuration takes place, while in SC1 reaction, racemization takes place. Okay. So in some cases, you can have SC1, SCI also can be involved. In some cases, carbon undergo bimolecular electrophilic substitution when it is attached to strongly electropositive species like metal. Okay. If it is attached to a metal atom, then the compound can undergo electrophilic substitution, bimolecular electrophilic substitution internally. Okay. Check. I write down here. Carbon undergoes bimolecular electrophilic substitution reactions. Electrophilic substitution reactions. When it is attached to a strongly electropositive atoms. That is mostly electropositive metals. Okay, mostly metals. So here you can say CR, something like mercury, Br. So you can have this type of system. Okay, when a reaction takes place with bromine, then you can have this type of substitution. So the retention of configuration takes place plus IsBr2 as IsBr2. Okay, so here this is a reaction occurs with retention of configuration. So here reaction occurs with retention of configuration. Okay, just like this SNI. Okay, so it is SCI configuration internally takes place. So here like early attack here, then it goes like this. So this is the another SCI internal reaction. So I'm repeating again, electrophilic substitution reaction can go like SC1, SC2, and SCI depending on the systems of the electronic systems. So carbon undergoes bimolecular electrophilic substitution reaction when it is attached to a strongly electropositive atoms, that is metal. So here we have. So these are very limited for aliphatic system. Now we just come to this electrophilic aromatic systems. Okay, So we have discussed about the aliphatic system. Now let's come to electrophilic aromatic system. Okay, the aromatic systems. So you can write electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reactions. Okay, so now let's come to this one. So in benzene is a consequence of the pi electrons above and below the plane of the ring is a nucleophile. Benzene acting as a nucleophile because of the electron pi electrons are delocalizing above and below the lone. So you can say that how benzene itself is acting as a nucleophile, Okay, nucleophile due to the delocalization of the pi electrons above and below the plane of the ring, So below the plane of the ring, of the benzene ring. Okay, so benzene is acting as a nucleophile. Okay, you can write this benzene structure, how these pi electrons are delocalizing above and below the plane of the rings. Okay, so here pi electrons we can have these pi electrons delocalizing above and below the plane. So we can have, so pi electrons are here, pi electrons are here, and the pi electrons are here. Okay, so these pi electrons are moving around this delocalized about this will be above the plane of the ring and below the plane of the ring. So that's why pi electrons are having. So another nucleophile coming. If this is coming, so this is repel each other. Electrons. The nucleophile is electron rich, and then benzene is also electron rich because of the pi electrons are delocalizing above and below the ring. So that's why the nucleophile, another nucleophile reactions cannot be take place in the case of benzene ring. That's why this mostly undergo electrophilic substitution reactions. Because I'm repeating again, benzene cell is acting as a nucleophile because of the pi electron delocalizing above and below the benzene ring. Okay, so aromatic systems we can have in the case of electrophilic aromatic substitution reactions. Okay, so here electrophile will be attached to the attracted the pi electron system. So the benzene ring cannot attract the nucleophile. So it can attract. So electrophile can attack the benzene ring. So like this, payload should be like this, and then we have an intermediate carbocation is formed. So here hydrogen are here, So we can have here first, then we have an carbocation is formed. Carbocation intermediate is formed. Then you can compare this with this is an aromatic system is lost here. So benzene has 6 pi. I'm repeating again. Benzene has 6 pi electrons delocalized in 6 delocalizing above and below the plane of the plane ring. So it's acting as a nucleophile. So any nucleophile can attack the benzene ring, so because already the benzene is already rich with the electrons. So it can undergo electrophilic substitution reaction. So electrophile can attack the benzene ring. So but first it is the benzene can undergo addition. However, this is substitution reactions. Benzene cannot undergo. So there is hydrogen here, only reacts with this X2. So this reaction for that benzene can have this X addition reaction. This is addition. reaction. So, but it doesn't go. So, benzene does not undergo addition reaction because addition reaction would yield a product that is not aromatic. So, this is the system. The product is not aromatic. So, it doesn't go addition reaction. So, benzene doesn't go addition reaction, but it goes substitution reactions. So, the product is here when the addition takes place, the product is not aromatic, so the reaction doesn't take place. But it can go this substitution reactions. This hydrogen is substituted by electrophile. Okay, so here electrophilic substitution reaction. So I am repeating again. I am comparing addition with a substitution reaction. So benzene is less reactive, is acting as a electrophilic substitution reaction, acting as a nucleophile, so it can attack to the electrophile. So electrophilic substitution reaction takes place, but addition cannot take place because the product form is not an aromatic. But in the case of substitution, here hydrogen is replaced by electron. So one hydrogen is by electrophile. So it is a substitution product is an aromatic system. Here it is the product is aromatic. In the case of substitution, the product is aromatic. Okay, so that's why benzene aromatic systems can undergo electrophilic substitution reactions. But however, benzene is less reactive towards electrophile than an alkene, even though benzene has more pi electrons. So benzene, I am repeating again, benzene is less reactive towards the electrophiles than the corresponding alkenes, because even though benzene has more pi electrons, because pi electrons of benzene are delocalized over 6 carbon atoms. I am writing here. Okay, benzene itself is less reactive towards electrophile than electrophiles and then an alkene. As compared to alkenes, benzene are less reactive towards the electrophiles. Even this benzene, even though benzene has more pi electrons than alkenes, than an alkene. Okay, so mostly alkenes undergo addition reactions, mostly undergo. So we can compare this with the alkene. We can compare this with a benzene and an alkene. In the case of benzene, the less reactive towards electrophiles, whereas alkene can react by addition. Okay, so it can take place. Why? So suppose why it is so? Because the pi electrons of benzene itself is less reactive, because the pi electrons of benzene are delocalized above the 6 carbon atoms. So increasing the benzene stability and making them less available for electron donation. Benzene itself is the pi electrons of the benzene rings are delocalized above and below the plane. So these pi electrons are not available, are less available for electron donation because they are already in the benzene ring, delocalizing the benzene ring. The 2 pi electrons are killed. However, in the case of alkenes, the 2 pi electrons are delocalized between 2 carbon atoms only, making them more electrophilic and thus more reactive towards more nucleophilic, thus more reactive towards an electrophilic than the delocalized electron in benzene. So I am repeating again, the 2 pi electrons in alkene are localized between 2 carbon atoms of the alkene, making the more nucleophilic and thus more reactive towards an electrophile. So for example, say in the case of alkene, R CH R, so electrons attack like this, electrophilic attack. So it gives a first a carbocation, then CH, okay, E, R, then again nucleophile attack, another nucleophile attack. So here positive charge, we can have this RCH, NU, RCH, R, E. Okay, so this is the addition types of reaction takes place. So here addition takes place with nucleophile addition product. So here addition takes place in the case of alkene, but in the case of benzene, it can undergo electrophilic substitution reactions. So we can have many reactions of the. Now let's have aromatic electrophilic aromatic substitution reactions. Different types of aromatic substitution electrophilic substitution reactions. So we can have electrophilic substitution reactions. In the general mechanism, we can have general mechanism of the electrophilic substitution reactions. General mechanism. First step is the electrophile. First step is the electrophilic addition. Electrophile attack here. Then you got a carbocation is fast form. So let's say hydrogen here, it's a hydrogen, and a carbocation is formed. Okay. So this carbocation can be delocalized like this. So we can have many resonance structures we can draw here. Is E, then this ice becomes positive charge here, then here is, then this will be becoming positive charge, then this we have this one, then again this delocalize this again. So we show that we can have many resonance structures that can be drawn. So many resonance structures of this can be drawn. So we have this and the hydrogen here, electrons here. Okay, so this composite charge here, again this. So in this way we can have draw this in the equilibrium form. Is E and then positive charge. So in this way they localize all this thing you can write. Okay. So we can write this from here to here. Okay. So then finally in the first, this is the first step for mechanism. First step. So electrophile attack to the benzene ring to give a carbocation. Then this carbocation can undergo finally this carbocation can loss of these electrons by positive charge will be so hydrogen loss of one electrons, I mean positive charge proton, loss of this one proton, then you can have this aromatic system will be returned back. So here like this. So here the product. So it is now aromatic. Now the product is aromatic. So I'm repeating again the second step. Mechanism of the. I'm repeating again the mechanism of the general mechanism of the electrophilic substitution reactions. The first step involves formation of a carbocation. These carbocations can be delocalized in all this system. So we can have this equilibrium form. And the second step that we have this loss of this proton, we got a product. So the product itself is an aromatic compound. So this about the mechanism of the reactions. So there are many types of reactions. You can have many examples. Many examples we can discuss about the electrophilic aromatic substitution reactions. So we can have halogenation, nitration, then this fragile clouds acceleration, etc. So we can have many systems, many examples of electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reaction. Okay, substitution reactions. Many examples we can do now. We get discuss generally for here. You can say number one, halogenation. halogenation. Then we can have second is nitration, then nitration, then sulfonation, then we have these Friedel graphs, alkylation, and then 5 Friedel graphs, acylation. Okay, acylation. So this can be discussed in the case of this electrophilic aromatic substitution reaction. So we can discuss these 5 systems. First one is halogenation, nitration, and sulfonation. So in case of halogenation, so here electrophile can be, in the case of here electrophile, so here E is mostly, here in the case of halogenation, E is equivalent to chloride and bromide. Halogen, X equal to, you can say halogen, E can be chloride, bromide, etc. But in the case of nitration, then E can be have nitronium ion, NO2. Then sulfonation, E can have this sulfonic group, SO3H. Then Friedel alkylation, E can be these alkyl groups. Then for acylation, Friedel acylation, the substitution reaction can be COR, okay, acyl groups. So these are mostly we can discuss in the electrophilic aromatic substitution reactions. So this will be discussed later on. So we will have discussed this general mechanisms or how the reaction takes place one by one in the next class. For today, let's wind up here. Okay. So we'll discuss in the next class. So I'm repeating again for the summarizing the today's class. So electrophilic substitution reactions can be generally replaced by RL, attacked by an electrophile, where IL is the leaving group. So we got a product, electrophilic substitution reactions. So electrophilic substitution reaction can be, electrophiles can be positively charged species like nitronium ion, bromonium ion, chloronium ion, etc. And alkyl positive charge also, acyl group also can take place. All are positive charge, and in some cases there may be also uncharged electron deficient species like BF3. And so then we can have aliphatic as well as aromatic compounds can undergo electrophilic substitution reactions, but mostly it is found in the reactions of aromatic compounds. However, an aliphatic electrophilic substitution reactions may undergo broadly classified as SE1, SE2. So this is for the aliphatic electrophilic substitution reactions, SE1, SE2. In the case when the transition state of the rate determining steps involve only one species, then it says SE1. And when the transition state involves two species, then it has to be SE2 reaction. So depending on the nature of the rate determining step, if the present one species, then it has to be SE1 unimolecular. It is involves two species, then bimolecular SE2. So it is just like earlier cases we have discussed in detail about the nucleophilic substitution reactions. Then we have SEO, the SEI also can discuss it. That carbon undergoes bimolecular electrophilic substitution when it is attacked with attached to a strongly electropositive atom, like for example metals. So we have discussed this also here. The retention of configuration takes place for SE1, SEI, like that. Then let's come to in the case of electrophilic aromatic substitution reactions, we can have discussed that benzene itself acting as a nucleophile because of the pi electron delocalized above and below the benzene ring. So another nucleophile that is having electron rich atom can attack to the benzene ring because benzene is already rich in electrons. So benzene itself is acting as a nucleophile. So it can attack with the electrophile. So we can have electrophilic substitution reactions. We can compare this with the alkane, with the aromatic system. In the case of alkane, reaction takes place addition product. However, in the case of aromatic system, it goes electrophilic substitution reaction, because addition product is not aromatic itself. So that's why benzene aromatic system undergo electrophilic aromatic substitution reactions. So we can have different types of substitution reactions like halogenation, nitration, sulfonation, Fajl-Krauss acylation, Fajl-Krauss acylation. So this thing will come discussed in the next class. Okay, for this today we wind up here. Okay.